Welcome, everyone. For today's prep, we're going to continue our discussion of the indeterminate form 0 over 0. And we're going to look at a few examples for how to handle this. And the first one we're going to look at is this limit right here. So we're going to calculate the limit as x approaches 2 of the function x squared minus 4 over x minus 2. Okay, so as with any limit that we're going to try to calculate, first thing we should do, try direct evaluation. So that's what we try first. So we try our direct evaluation. Let's see what we get. Give it a try. All right, so, and by direct evaluation, we take the number that x is approaching, and we're just plugging it into the function that we're considering here. So if we try our direct evaluation, let's see what we get. We get 2 squared minus 4 over 2 minus 2, which ends up being 4 minus 4 over 2 minus 2, which is 0 over 0. Okay, so this 0 over 0, this is the form that we're kind of running into now. So this is not the answer. This is never the answer. But what's going on here, the fact that we're getting 0 in the numerator tells us that there's something we can factor out of the numerator. And the fact that we're also getting 0 in the denominator tells us that there's a factor for the denominator. So there's some factors in both the top and the bottom here that we might be able to cancel off. And that's going to be our main strategy here. So first of all, this is not the answer. This is kind of like a dead end, but it does kind of give us some indication of where we can go. So what we're going to do instead, kind of try this again. And instead of plugging in immediately, we're going to try to factor our rational function here as much as we can. Try to factor the top and the bottom. All right, so let's write this out fresh. We got our limit, x is approaching 2, x squared minus 4 over x minus 2. And we're going to try factoring that numerator. And it turns out it factors nicely. It factors into x minus 2 times x plus 2. And then we've got our x minus 2 in the denominator. And again, the fact that we're getting 0 on the top and 0 on the bottom, especially for rational functions, is an indication that we should be when we factor, we should end up with a same factor on the top and a same factor on the bottom. Okay, so that's the first thing here. We're trying it again, but now we're factoring. All right, so the top here has x minus 2. The bottom here has x minus 2. Next step, we're going to get rid of those. We're going to cancel them out. So these would cancel. So that's our next step. Cancel those out of there. And what we're left with then, after we do that, is just x plus 2. And as soon as we do this canceling step, as soon as we cancel out those kind of factors, those offending factors that were given us 0 and 0, as soon as we do that canceling step, then we retry direct evaluation with all the stuff that we have left. And when we do that, well, we're gonna finish it off. So now we try direct evaluation again. If we get a number that makes sense, good, we're done. If we get another 0 over 0 or something else, well, then we deal with that. But we try direct evaluation again, and in this case we get 2 plus 2, which is 4. So we just do our direct eval. And there we go. We got the limit there. It's 4. All right. So it's a technical point. I want to look at this canceling step just a little bit further. It's a technical point, but technically, before we canceled this out, this function and this function are technically different functions. Now, we mentioned this in class, and I want to go back. We looked at these two graphs, and we had this one graph, we called it f of x, that had a kind of a little hole there at x equals 2. So it was technically undefined at x equals 2. And then we had this other graph that looked like a line. We called it g of x. Well, this is the graph, this first one here, this is the graph of x squared minus 4 over x minus 2. And the graph in the second graph there, that's the graph of what happened after we did the canceling, the function that we had after the canceling. So this is kind of like the before canceling function, and this is the after cancel function. And what we see here is that they, for the most part, are the same function, except they differ at that one specific x value. This function is undefined at x equals 2. This function is defined at x equals 2. So technically, these are two different functions. But because they agree everywhere else, the limits are the same. So this limit property that we talked a little bit about in class allows us to kind of cancel off those factors that give us the 0 over 0. And we can go from a more complicated function to the canceled off version that's a little bit easier. Okay. So, not too bad. Let's try another one. Get a little practice here. So, we're going to do the limit of 5 plus h squared minus 25 all over h as h approaches 0. So our variable here is h, but the idea is going to be the same. Now this is another type of thing where, maybe we could factor this off right away, but maybe it's not altogether obvious how this would factor. So another strategy, we will get into factoring here. So factoring does, come into a lot of these. But it might also be helpful to just multiply this 5 plus h squared out. But before we do that, first thing we should try, we just try our direct evaluation. See if you get a number that makes sense. If you do, you're done. So let's see what we get. So h is approaching 0 here. So let's plug h equals 0 into our function here. Let's see what we get. So we get 5 plus 0 squared minus 25 all over 0. Well, already tell there's going to be an issue here. So it might be an infinite limit, but let's keep going. And if we simplify, we end up with 5 squared minus 25 over 0, which ends up being 25 minus 25, or 0 in the numerator there. So again, that's not our answer. 0 over 0 is never the answer here. But it's worth a shot. Try direct evaluation first. If you get a number that makes sense, well, then you're done. All right, so what are we going to do again? Well, we're going to start fresh. So we try it again. And this is where algebra comes in. So let me just write out the limit. H is going to 0. 5 plus h squared minus 25 all over h. And we could factor this right away, but it might not be obvious how to factor that. Maybe it is. So another kind of way to do this is, let's try multiplying this out. This is more of like a kind of a brute force attack here. We're just going to do what we can do. All right, so if we multiply that out, and if you need to, let's go off to the side. We got our 5 plus h times 5 plus h. That's what we're doing there with the squared. And then we distribute the 5 to both terms in the second piece there, and then we distribute the h to both terms in the second piece there. So if we multiply that out, when we do the 5s, we get 25. And then we end up with 2 copies of 5 times h. So that's going to be plus 10h. And then when we do the h and the h, we get an h squared. So we just multiply that out. And then we've got our minus 25 all over h. And we want to be careful with notation. So I'm missing something here. I'm missing my limit sign. So every step that we do these things, I want to include my limit sign until I actually do the direct evaluation, and then no more limit sign. So I got to kind of squeeze it in here. We need the limit as h goes to 0. All right. What can we do? Now we look for things to simplify. So if we notice, I can do the subtraction, and the 25s get canceled, so that's kind of nice. So let's write down what we have. So I have 10h plus h squared all over h as h goes to 0. And now we're ready to kind of factor. So there's an h in the first term. There's an h in the second term. I can factor out an h in the top. So I get h times 10 plus h all over h. And then, bang, the h's cancel. And so what we're left with then is just the 10 plus h. After all the dust settles there, we've got just the 10 plus h. So we did our factor, and then we did our cancel. So we did those 2 steps. And then as soon as we do that cancel step, then we can just do our direct evaluation. So h is approaching 0. Well, then we can plug in our h equals 0 into what we have left. And we end up with 10 plus 0, which is just 10. And there's our direct evaluation. And notice, every step, I've got my limit sign until I do that direct evaluation. And the reason why, well, first of all, the limit sign's telling us we're kind of interested in where are we going. So this is saying, like, where are we going? Where's this function going? Where is this function going? Where is this one? And so on. And then once we do the direct evaluation, that's actually the destination. So we've reached our destination here. So we know where we are. So we don't need the limit sign in front. And then same thing, if we left off the limit sign, this function is technically, well, this function, once we cancel off the h's, is technically different from this function. So if we're just going through and not including our limit sign, and we're just saying all these things are equal to each other, well, that's not entirely true. This function is not the same as this function. But because of the way limits work and of that special limit property, even though these 2 functions are technically different, their limits are the same. Their limits are equal. So we want to be precise in our notation here. So limits at each step until we get to our destination, and then we're good. Okay, so we're gonna practice this. Oh, and one more thing I want to mention. You could think of it like this, factoring an h out of the top. But if you wanted to, another way to think of how to simplify from here to here is you could just instead imagine dividing each of these terms by h. So we could divide that first term by h, and then the h's cancel there. And then we could divide that second term by h, and then we're going to have that one extra copy left. So another way to think of that. All right, so we'll get some more practice in class. So we'll see you then. Bye-bye.